This is what I wanted them to look like. I want the protons in the middle. I want the neutrons in the middle to symbolize the nucleus. So there's going to be 4 protons in beryllium, 5 neutrons in beryllium, and there's going to be 4 electrons because it's an atom, and so the protons and electrons are the same. So the inner shell can hold 2. So there's half, and now it's paired. And then we have our next shell, and we need to hold 2 more. This shell can hold 8, and so we don't pair them until we've already got 4 down there. This is what your Bohr diagram needed to look like for beryllium. Nitrogen would look similar. Nitrogen is going to be P equals 7, N equals 7. 1, 2, 3, 4, 5, 6, 7. There's nitrogen. Oxygen's going to be P equals 8, N equals 8. 1, 2, 3, 4, 5, 6, 7, 8 is what that thing's going to look like. Now, once you've got the 4 down there, it doesn't matter where these next 2 go, like where you choose to pair them. I could have put them here and here. I could have put them there and there. But you don't start, you put 1 at 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock, or the points on the compass, north, south, east, and west, and then you start to pair them. And it does actually matter, because where you go from, assuming you go on in chemistry, it's related to concepts you'll look at later. Sulfur is going to look like this. P equals 16, N equals 16. So this one's a little bit bigger. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Neon is going to look like this. P equals 10. N equals 10. Wow, I picked a whole bunch where the protons and neutrons are the same. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Dominic, good morning. When you're late, hurry a little bit. Where are you on my list? Right there. Boom. Calcium's going to look like this. Again, same. P equals 20, N equals 20, and calcium is the absolute worst one I could give you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because it's huge. 11, 12, 13, 14, 15, 16, 17, 18. That ring is full. 19 and 20. Comments, questions, concerns on any of those? Okay. If that was nice and easy, that's great. If you didn't get a chance to practice, there's going to be an assignment that you're going to do related to these things, and if not today, then Monday. Okay. The ions, if we flip the page, the ions are going to look like this. Remember, the ions are charged, so now we actually need to look up on the table and see what the charges are. Chlorine. P equals 17. N equals either 18 or 19, depending on which periodic table you're using. I'm using the one on the inside front cover, so that's going to be 36, so that means N is going to be 19. And the atom of chlorine would have 17, but if you take a look at the table, chlorine is going to have, the ions always get these square brackets, a charge of -1, which means the chlorine ion is going to gain 1 more electron. So if it starts with 17, gaining 1 more means we're going to have 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. The lithium ion's a lot easier. P equals 3, N equals 4. The lithium ion, again, if you look at the periodic table, has a charge of +1. So to become charged +1, what does an element have to do? Or an atom have to do? It's going to lose 1. So square brackets, put the charge. And now because it's a +1, we have to have 1 less electron. So we're done. 3 minus 1 is 2. Phosphorus. Oh boy. Here we go. P equals 15, N equals 16. And phosphorus has a charge of -3. That means phosphorus, the atom would have the same amount of electrons as protons, so the ion is going to gain 3 electrons because it's got this negative charge here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Another shell. 11, 12, 13, 14, 15. That's where we'd stop in the atom, but we don't have an atom. We've got an ion. So 1, 2, 3 more, and we're done. Three more. Sodium. P equals 11, N equals 12. It's an ion, so we're going to throw the square brackets down there. The charge on sodium is +1, so it's going to lose 1 electron. It would have had 11. Now losing 1, it has 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Magnesium is going to look similar. P equals 12, N equals 12. It's an ion, so throw down the square brackets and the charge. And now we can go ahead and... Okay, what does that even mean? My grade 9s have been trying to get me to say it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're done. There should have been 12 plus 2 means we've lost 2 electrons and we're done. There are far too many of you writing, which means there are far too many of you who did not practice this yesterday. The aluminum ion looks like this. Where is the aluminum ion? P equals 13, N equals 14. It's an ion, so square brackets and the charge. The aluminum atom would have the same number of electrons as protons, but we have an ion, so it's a +3 charge, which means we have lost 3 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're done. Now, there are some shortcuts to this that I didn't want to show you until you'd practiced it kind of the ugly long way. Did anyone notice any of the shortcuts? Anything interesting as far as the atoms or ions went? Perhaps you did. Hey, look, there's this interesting little result. Nobody noticed anything fun and interesting? That's fine. That's why I'm here, to show you the fun and interesting little things. Okay, so you don't have to flip back, but I'm gonna. I want you to notice something. With beryllium, nitrogen, and oxygen, each one of these guys has how many electron shells? 2. Where are they on the periodic table? What does that mean? 2 what? Groups go up and down. Columns go up and down. The row. Interestingly, they have, each of them have 2 shells, and all 3 of those, beryllium, nitrogen, and oxygen, all in row 2. Interesting. Let's look at the next ones. Sulfur and neon. Sulfur and neon. Oh, neon's another one. Neon also had 2. Look, there it is. Row number 2. Sulfur, 3 rings. Where do you think it might show up in the periodic table? Row number 3. So there's a relationship between where these things are in the periodic table and what their Bohr diagrams actually look like. It's like someone did it on purpose. Calcium is, or has 4 shells. And look, there it is in the 1, 2, 3, 4th row down. So there is a relationship that exists between where these things are on the periodic table and what their Bohr diagrams actually look like, which is interesting. So we can include that as part of our shortcut here. So 4 atoms. When you're drawing, if I ask you to draw a bunch of Bohr diagrams, a really easy way to shortcut the Bohr diagram is instead of counting out electrons every time, you can just figure out what row you're in, and that's how many electron shells the atom's going to have. So the electron shells, the electron shells are going to equal the row number for an atom. What does that even mean? There's something else interesting that shows up on the periodic table as far as these things are concerned. I'm going to flip back to the atoms. I want you to see if you can notice something else. The electron shells, the number of the electron shells are going to equal the row number. And there's another neat relationship between some other feature of the Bohr diagrams and some other part of the periodic table. Let's look at oxygen and sulfur. What do these two, put your phones away, gentlemen, I can hear that, have in common? How are oxygen and sulfur related as far as their Bohr diagrams are concerned? There is a similarity between these two, yes. Neither of them have full outer shells, that's true. How many are in the outer shells for both of these? Count them again. For these two, specifically. There's 6. Neither of them are full, and they have the same number. Both of them are 6. Fascinating. What column are they in? Nope. Close. What column are they in? No, I'm looking at you, man. You're the one that said it. They're not in column number 6. Oxygen and sulfur are right here. They're in column number 16. Interesting. Nitrogen. Nitrogen has 5 outer electrons, also not full. It's in column 15. Beryllium has 2. It's in column 2. Neon has 8. It's in column 18. Calcium has 2. It's in column number 2. There is a relationship between what row you're in the electron shells and what column you're in and how many electrons are on the outside. So you can shortcut all of this and don't actually have to count anything by having it look like this. Let's go back and I'll write a shortcut down here for you. The electron shells are going to equal the row number. The outer electrons are going to equal the, we'll say the ones place in the group number. And I'll demonstrate for you what this shortcut looks like and how it makes your life so much easier. An example of this shortcut is going to be this. Let's pick one we haven't done yet. Nickel. What number is nickel? I don't think I like nickel. Pick a number between 1 and 20. 1 and 20. Number 19. Okay, here we go. So he wants potassium. And we're doing an atom. What row is, so potassium, we start with the, as always, start with the nucleus. There are 19 protons because the atomic number is 19. There's going to be 20 neutrons. because the mass is 39. 39 minus 19 is 20. What row is it in? I mean, there's a PR table up on the front, too. Potassium's letter K. What row are we in for potassium? The fourth row. 1, 2, 3, 4. And what column are we in? Column, not row. Columns go up and down. We're in column 1. So that means there's going to be 1 in the outer shell. What do I do with all of the shells underneath that one? Sorry? Fill them up. First one holds 2. Next one holds 8. Next one holds 8. There's no counting. I mean, we could count just to make sure we did it right. 2, 4, 6, 8, 10, 12, 14, 16, 18, 19. It's a lot quicker if you can use the information given to you on the periodic table to crank these suckers out. It's still a lot of work. Bohr diagrams suck to draw. There's no doubt about that. But they're a lot. It can be a lot quicker if you notice some of the things, some of the power behind how the periodic table was developed, which is something that you would have looked at and you're supposed to look at in grade 9, how they invented or how they came up with the ordering for the periodic table. So that's the atom. That's really where the shortcuts power is for drawing these for atoms. We'll do it for the ions too. There's shortcuts there as well. Take a look at all 6 of these pictures, these Bohr diagrams that I drew. What is interesting about all 6 of these diagrams? Yeah, Jihad. All of them are full. Interesting. The ones that are positive lost electrons to become full. The ones that are negative gained electrons to become full, but they're all full. So maybe there's something to it, right? So a part of the shortcut for ions, here's your shortcut. All shells are full. Always. When you're drawing Bohr diagrams for ions, every shell has to be full. That's how these things become ions. The other piece to remember here, though, is what happens when these things gain and lose. So I'm going to pull out the periodic table again. Let's look at these positive ones. There's 4 of them. Lithium, sodium, magnesium, and aluminum. Lithium is right there. Lithium, sodium. Is it those 4? Magnesium and aluminum. Okay. Lithium is right there. Sodium, magnesium, and aluminum. So let's look at these bottom 3. Sodium, magnesium, aluminum. They're all in row 3. So the atom would have 3 shells. But look at sodium, magnesium, and aluminum. How many do they have? 2. Where'd that outer shell go? Those were the electrons that got given away. Sodium lost the 1 it had in the outer shell. Magnesium lost the 2 it had in the outer shell. Aluminum lost the 3 it had in the outer shell. So the ion shortcut is a little bit more involved. For ions, all shells are full, and positive ions have 1 less shell than row number. And the negative ions have the same shells as row. But that top point there, all shells have to be full when you've got an ion, is the key piece there. So potassium's really big, and I don't have a lot of space there. So I want to pick a smaller one that we haven't done yet. Let's look at fluorine. No, let's not do fluorine. What have I not done yet for an ion? Did we do a beryllium atom? Yeah, let's do a beryllium ion. Here's my example for the ion. We're going to do a Be ion. Beryllium's up there in the top left. How many, if it's an ion, how many shells should it have? What row is it in? What row is it in? What row is it in? It's in row number 2. What kind of ion does it form? Positive. So it's going to lose one of those two. So how many should beryllium have? Only have one shell. So a beryllium ion is going to look like this. P equals 4. N is going to equal 5. Because it's an ion and it's positive, it has one less shell than row number. So it's in row 2. So it's only going to have one shell. Boom. And that shell's got to be full. That's a 4. You still have to put the square brackets. You still have to put the charge. Jihad, did you get your booklet from your friend? Excellent. I didn't even see you leave. Hold on. There it is. So the shortcuts exist. Absolutely use them. I mean, if you don't want to, that's fine. I'm just trying to make your life easier. You want to count everything out every time? Go for it. But I will recognize Bohr diagrams are terrible. And I'm not the first guy to recognize that Bohr diagrams are terrible. There was a guy who came after Bohr who said, Bohr, your diagrams suck. Let's make them cleaner. And I'm going to show you those perhaps today, but if not today, then definitely tomorrow. By tomorrow, I mean Monday. So that's Bohr diagrams. We're going to use Bohr diagrams now, flip the page, and we're going to start building compounds. We're going to do stuff with them, and they're going to give us an idea of how chemistry actually works. Here we go. So, there are different kinds of compounds. As you go off into chemistry, the first way we classify what you're working with in chemistry is by identifying what kind of compound you have. What's a compound? So this first blank is here. A compound is made up of atoms. Shocker. Everything's made up of atoms. But to have a compound, you would have looked at this in grade 9 when you were talking about different classifications for matter. You would have talked about elements and atoms and mixtures and homogeneous mixtures and heterogeneous mixtures. What is a compound defined to be? Who remembers? Some good guesses. So if you're looking at the periodic table, everything you see up there is a pure element. Even if you have a whole bunch of the same kind of atom, it's still considered pure element. You can go out into the world, and at one point it was a lot easier to do this, but you can go out into the world, you can dig in the ground, or you can sift through silt in a river and find pure gold. This is what started the gold rush that brought a whole bunch of people up here to the Fraser Valley, brought a whole bunch of people to the Yukon, brought a whole bunch of people to Alaska. There's value there. But what you're seeing there, it doesn't matter how big or little the thing is, it's pure gold. Because the only atoms contained in that nugget are gold atoms. To become a compound, what you have to have is 2 or more different elements, and they need to be bonded chemically. And that can be hard to tell at this stage if what you're looking at is a chemical bond or if it's just, hanging out together. I mean, it's fundamentally no different than human relationships too, right? You're hanging out with someone. Are you friends? Are you together? Is that ambiguous, awkward in between? Has the relationship not been determined yet? Do you have to have a conversation? Until you really study the chemistry, it's hard to know. It's functionally no different here, right? So a compound is made up of two atoms that are bonded chemically, and what bonded chemically means, this piece here, means there has been an exchange of electrons. And that can look like a few different things. Again, not necessarily functionally different than people. So the two different kinds of compounds are ionic compounds and covalent compounds. Does anyone remember talking about these different kinds of compounds in grade 9? Has this language been used before? Okay, cool. What is an ionic compound? Or do you just remember that it was mentioned, but you don't remember the definition? Because that's cool, too. You remember the definition? What's the definition of an ionic compound? And? Yes? Ooh, that's the other one. The covalent one is the one they share. Dominic, the ionic ones are the ones that give and take. So in an ionic compounds, this is a give and take of electrons. And in a covalent compound, this is the sharing of electrons. You guys have identified both of them. So let's define these further. An ionic compound is a compound made up, the only way that there's a give and take of electrons is you have to have oppositely charged ions. Positive ions give electrons, negative ions take electrons, and so if there's an exchange, you need both. One of each, or a couple of one and one of another. These bonds are always between a metal, because the metals are the ones that become positive, and a non-metal, those are the ones that become negative. The metal, which is always positive when it ionizes. Zoom in a little bit here. Gives one, sometimes more of its electrons, which we can shorten it to be E minus. You need to recognize what that means. Electrons to the non-metal. The non-metal is a taker. It wants everything. We all know people like this. Metals are givers. We also know people like this too. There are people who will give, and there are people who will take. Ionic bonds are strong. You guys would have learned in the physics portion of Science 9. What holds ionic compounds together? What do oppositely charged things do? Which one is it? Oppositely charged objects will attract each other. Like charges repel, opposite charges attract. So a bond, an ionic bond, is a strong electric attraction. There is not enough space to write those words. I apologize. Electric attraction that forms between oppositely charged ions. Atoms lose or gain electrons to form ions that have full valence shells. That is the name for the outer shell. And are therefore more stable. One of you mentioned yesterday the existence of this octet. You would have learned this in grade 9. You should have learned this in grade 9. If you didn't, I'll explain what it means. So here's how this happens. I've given you the picture so that we don't have to draw them all out. Save some time. A sodium atom. Here's a sodium atom. There's 11 protons, there's 12 neutrons. In the sodium atom, then, there needs to be the same number of electrons as protons. If there's 11 protons, you're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now take a look at what we've got here. Sodium's got 1 electron in its outer shell. Is it going to be easier for sodium to give up that 1 electron or to take a whole ton of electrons and fill that outer shell? To give the 1. So that's why metals do what they do. They have fewer, what was that? Weird. In their outer shell, and so they give. They're happy to give. So what this guy's going to do is he's going to give 1 electron to empty the valence shell. And how you're going to demonstrate this is you're going to, because I'm going to get you to draw this process. You're going to connect an arrow, just like this diagram has done, showing the one that has left and placing it where it needs to go. This is why it matters how you draw these atoms. Because you take a look at the chlorine one. The chlorine atom has 17 protons, so the atom has to have 17 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. There's 1 electron that's not paired. And so when sodium gives up the 1, it's going to have to pair with the the lone electron in chlorine. Chlorine's going to have a full outer shell then, because ions will always have a full outer shell. He'll be happy. He'll be happy. So then these guys are electrically attracted together. And now you don't have sodium and chlorine. You have table salt. It's weird. That's how it goes. So sodium's going to give 1 electron. Chlorine is going to take 1 electron to fill. When you draw the ions, because the sodium gave it away, it's positive. Because the chlorine took, it's negative. So there's going to be the electric attraction between positive and negative, which you would have looked at in the physics section of grade 9. Opposite charges attract. So that's ionic. Covalent is the other one that you identified. Covalent is a sharing. So why do you share something? Sharing only happens when? Why might I tell my children to share an object? When there's not enough of something as part of it, and there's another piece to it. No. I'm talking about my kids. I want you to talk about my kids too. When might I tell my children to share? One part of that is there's not enough of something. And both of them all, whether benefit is debatable, very debatable, but both want. When there's not enough of something and both of them desire the object. This happens in my house all the time. They love Where's Waldo. We have Where's Waldo books, and they always want the same one, and they don't want to look at the same page. Not enough Waldo, and they both want. So a covalent compound is the same. Something has to be involved in the sharing here. So the only time sharing happens is if both want. Okay, what kinds of what kind of ions form because an object wants to get something? Which ions take? Sorry? Which ions do the taking? Non-metals. They have space, like this chlorine right here. This chlorine wants to take. It wants to fill the space. Sodium is happy to give. Sodium does not want more. There's no sharing here because chlorine walks up and says, may I? And sodium says, yes, please, I don't want it. There's no need to share. But if you've got a bunch of chlorines and this chlorine says, I want, and this other chlorine says, I also want, now we have an issue. So covalent compounds, the sharing only ever happens between nonmetals, and that's what this blank is right here. A compound that results when atoms of two or more nonmetals bond. Because the nonmetals want to gain electrons. All nonmetals want to gain electrons. So then what happens? A covalent bond is a strong attraction between atoms that form when atoms share valence electrons. And so there's a diagram here. It's not a very good one because the photocopier didn't draw everything I wanted it to draw. So I'll show you in a little bit more detail what this thing looks like. There should be a ring right here. You guys can add that one in. And there's going to be a ring right here. And that's a water molecule. Why does a water molecule form? Well, let's draw these things out, shall we? Here's oxygen. In oxygen, P equals 8, N equals 8. So the Bohr diagram for the atom is going to look like this. 1, 2, 3, 4. There's 8. Sorry, there's 8. 1, 2, 3, 4, 5, 6, 7, 8. There's oxygen. Oxygen has space for 2. Hydrogen's a complicated one. Here's hydrogen. P equals 1, N equals 0. P equals 1, N equals 0. Water is H2O. So we need 2 hydrogens and 1 oxygen. Now, hydrogen is interesting. Hydrogen's a little complicated because what are the 2 ways that hydrogen could be happy, as an ion? It could give up this 1 electron and just become a single proton zipping through the world. Or it could take. This inside shell has room for 2. And so it could take an electron from something else. What hydrogen will do every time is if hydrogen is interacting with a non-metal, so oxygen, it wants to take. For whatever reason, that's what hydrogen does. So you have a hydrogen atom, 2 hydrogen atoms, they both want. There's an oxygen atom, it wants as well. And so what happens is they say, okay, well, I want and you want, so let's just get close together and share the book. If we're going to go back to the Waldo analogy with my children. They have to sit side by side and deal with the fact that both of them now are going to possess the book together. At daycare, that my children were at my daughter was at for the last 2 years, sometimes there was more than 2 children. Sometimes there was 3 children. And all of them want. So they have to be in proximity together, sharing the object that they want. So what happens is, it's not a give. When you're drawing a Bohr model for the giving, we draw the arrow, and it's done. The electron has gone. Here, that doesn't happen. This is how we demonstrate the sharing. Oxygen and this hydrogen are going to share those 2. Oxygen and this hydrogen are going to share those 2. And then you actually have to go ahead and redraw the thing, putting them close together and having them share. So this hydrogen is going to have a ring that looks like this. This hydrogen is going to have a ring that looks like this. But up right next to the oxygen that's there as well. And so looking at the Bohr diagrams, this can help us understand why the elements do what they do. Why do they form compounds? Well, because they have space. Some have space to give electrons, some have space to take electrons, and so they're going to arrange themselves. There's a whole section of chemistry that is just studying how compounds arrange themselves. It's absolutely atrocious, but there's a lot of money to be made. So if you're sitting there saying, I just want a job that pays a ton, the field that you want to study is organic chemistry. It is barbaric. But there it is. Okay, so let's figure out how we're going to draw some of these things, and then I'm going to let you play. Okay, first thing we need to do is we need to identify what kinds of compounds we have so we know what kind of Bohr diagrams we have to draw. So there's 8 of them there. We're going to label each one of these as either ionic or covalent. Ionic means you've got a metal and a nonmetal. Covalent means you have a nonmetal with a nonmetal. So let's do these together. The very first one is already kind of screwy. I've got O2. That little 2 means I have 2 of something, and the O is the symbol that I have. The symbol O stands for oxygen. So if I have 2 oxygens butt up next to each other, is this going to be ionic or covalent? It's going to be covalent. Oxygen's a nonmetal, and I have 2 of them. You can either write out the word covalent or just put a big letter C. If you'd like to be a little lazy, just put the first letter. Okay, I've got NAF. What kind of compound is that going to form? Well, is it a metal nonmetal or is it non-metal nonmetal? What is sodium? Sodium's a metal. It's on the left-hand side of the periodic table. So it has to be ionic. If one of them is a metal, it has to be ionic. You don't even have to look at the other one, because compounds don't form between a metal and a metal. Okay, next one. What's calcium? It's a metal, so this thing has to be ionic. H2O, I've already told you. It's got to be covalent. Hydrogen could go either way. When it's with a nonmetal, it's always covalent. This guy here, what's aluminum? It's a metal. It's on the left-hand side of the staircase, so this guy's going to be ionic as well. What's beryllium? It's a metal, so it's going to be ionic. Bromine is? It's a nonmetal. And fluorine is a nonmetal. They're both on the right-hand side. So it's going to be covalent. And then AsBr4. Where is As? What side of the staircase is it on? I'm seeing fingers point to the right. On the right-hand side means it's a nonmetal. And bromine is as well. So this is going to be a covalent compound as well. Identifying is the first part of the battle. Once you identify them, then you can know how to draw these things. I'm going to draw 2 as examples, then I'm going to let you play. Here we go. We're not going to just draw Bohr diagrams now. We're going to draw Bohr diagrams of compounds. It's going to be great. Here we go. When I ask you to draw Bohr diagrams for a compound, the first thing you need to determine, step 1, is determine if the compound is ionic or covalent. That'll tell you what happens with the electrons. So I'm going to do 2 examples for you. We'll do an ionic one and we'll do a covalent one. Always draw the Bohr models separately. And then show how these things transfer. If it's ionic, you're going to show the transfer of electrons with an arrow. And then redraw. If it's covalent, you're going to show the sharing. And then you're going to redraw. The ionic ones you'll redraw with brackets. The covalent ones you'll redraw overlapping those shells. No brackets needed for a covalent compound. Do 2 examples and I'll let you play. LiF. What is that? It's ionic. Why is it ionic? You were right the first time. It is ionic. I wrote it down. I'm committed. Because it's a nonmetal and a metal. Which one's the metal? Lithium. So let's draw these things. A lithium Bohr model. Okay, let's use the shortcut. It's in row number 2 and column number 1. So lithium's going to look like this. P equals 3, N equals 4. The atomic number is 3. 7 minus 3 is 4. It's in row number 2, so 1, 2. And it's in group number 1, so it has 1 in the outer shell. The inner shell is full. There's the Bohr model, all nice and shortcutted. I've got fluorine. Fluorine is atomic number 9. So the protons are going to be 9. It has a mass of 19. So to find the neutrons, we take the mass and we subtract the atomic number. 19 minus 9 is 10. Fluorine is in what row? Row number 2. So 1, 2 shells. And it's in column number 17. So it's going to have 7 outer electrons. 1, 2, 3, 4, 5, 6, 7. Every other shell on the inside is full. So there's the shortcut version of my Bohr diagram. Now, because this thing's ionic, we need to draw the transfer. This electron is going to go away, and where's it going to slot in? Right there. As a bunch of you pointed. So, draw the arrow. Boom. There it is. Having different colors really helps here. And now we redraw. Our lithium is going to look like this. P equals 3. N equals 4. And it's only got the one ring because it gave away that electron. It's got a charge of positive 1. The fluorine, also an ion. It's got a charge of minus 1. So P equals 9, N equals 10, and you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you're done. The formula will tell you how many you need to draw. LIF, there's no numbers, there's no subscripts down here, so we just need one of each. I'm not going to do it for you. I'm going to let you do it in a second. If I'd given you this formula, what if I'd given you MgF2? What would you have had to draw for this guy? What does that little 2 down there mean? You whispered. Can you say that a little louder? You would have had to have drawn 2 fluorines and 1 magnesium. So this would have been 1 Mg and 2 Fs. You would have had to draw 3 things and then arrange them. Okay, when you're ready, flip the page. I'll do one more example. So that's what ionic looks like. It only makes sense for me to do one more. Let's draw the Bohr model for O2. We already said that O2 is covalent. It's 2 oxygens. So be nice and easy. Draw 2 of the same thing. So my first oxygen is going to look like this. Oxygen's atomic number 8. So it's got 8 protons. The mass is 16. 16 minus 8 is 8. So there's 8 neutrons. It's in row number 2. And it's got 6 in the outer shell. Now, careful how you do this. You want to be smart about how you draw these things to make your life a little bit easier. This is the, I'm going to have to draw another oxygen right here. So when I'm doing the 6 in the outer shell, after I've drawn my first 4, it's going to make sense for me to go backwards to pair these 2, because I'm going to have to draw another oxygen right here, and I want the electrons that I'm going to have to pair up to be close to each other, because this is going to be my other one. P equals 8, N equals 8. It's going to have 2 shells because it's in row number 2. It's in group 16, so it's going to have 6 in the outer shell. Both of them need to have full inner shells. So when I drew the one on the left, I put the 2 electrons, the lone ones, on this side. When I drew the one on the right, I put the 2 lone electrons on the inside, just to make my life a little bit easier. Because this thing's covalent, there's going to be a sharing. It's not a transfer. So you circle up the place where these 2 things are going to share. Oxygens are takers, not givers. They both want Waldo. And so now we go ahead and we redraw. These are the ones that are terrible to draw. I'll be honest with you. Because they're big, they're kind of clunky. We have to figure out a way to draw them close enough so that the outer shells here overlap, but I've still got room on the inside. So it's going to take some practice. Sometimes it helps. Let's overlap the outer shells first to get a picture of where we're going to put these things, and then we can fill it up. We're going to put the P equals 8, N equals 8, P equals 8, N equals 8. We need another ring on the inside for that inner shell. These electrons here and here are going to be that pair and that pair. The inside is full. This pair and this pair are going to be this pair and this pair. The only awkward part now is I have to draw these two shared and these two shared. So 2 of them are going to go here, and 2 of them are going to go here. And that's what your covalent compound is going to look like. Comments, questions, concerns about what I've done? Okay. If there are no questions, I have 5 questions I want you to practice. I'll help where needed. If you want to work on the whiteboards, by all means, feel free to work on the whiteboards. I encourage you to discuss this. Talk about it with the people that you're sitting with if you're stuck on something. Ask me for help if you've got it. There's 2 questions here, MgO and Cl2. And then if you flip the page, there are 3 more, BeF2, H2O, and Li2O. Play with these things. And then on Monday, I will show you an easier way to do these, because there was a guy who came after Bohr who said, Bohr, this sucks. Let's do less work. So that'll be Monday's lesson. On your market set giver, if you got questions, let me know.